Dr. Xu Hongjie from ThEC12.
Yeah, ThEC12 is Shanghai Institute of Applied Physics. It's one of the 100 institutes among the Chinese Academy of Sciences in the nuclear science and founded 50 years ago. The institute began the thorium energy from the 1960s. The research lasted about 40 years. In 1970s, just because of the thorium application, the institute began to make research on the molten salt reactors. The first effort is to build a non-power cold state, the molten salt reactors, which reached the critical in 1971. And because of the limitation and ability of the industry and the technology in China, this project had been stopped and turned to the light water reactor. Later, middle of the 1990s, the institute began to pursue a synchrotron radiation facility. And it took about more than 10 years. Finally, the first SSRF, Shanghai Synchrotron Radiation, had been successfully constructed and now it has been open to user. Just the last 10 years, the energy problems and CO2 emission become too big challenge to the world and also to the China. Under the approval by the central government, CAS will start initial so-called the research program. There are two parts. One is the so-called thorium molten salt reactors, which is a long-term program. It's aimed to develop some technology, including to the reactor technology and the chemical separation technology and so on. Finally, to realize the usage of the thorium as a nuclear fuel. The TMSR is a thorium molten salt reactor with both solid fuel and liquid fuel. First is Y TMSR. Here is a slide from Carlo Rubio. He gave a presentation in China. He just said that China's the thorium natural reservation maybe is top one in the world. There are many, and can be used for many years. About 20,000 years, okay, estimate. In China, there are many thorium, much more than uranium. This just shows that if you want to do some breeder, you have to meeting these conditions at larger and equal to. And this area, it's a so-called thermal region, and resonance region is so-called molten salt reactors working region. It's more suitable to thorium fuel. And the typical molten salt and built by the Oak Ridge 40 years ago. American scientists have been working on the molten salt reactors for the different aims for many years. From the 1940s up to the 1970s. At first, it's for the iron bomb, and then transferred to the civil applications. And the MSRE have been built and operate successfully for almost 5 years and accumulate many result is a basic in scientific base of our today for the MSR and many kind of the MSR discussion. And they have still, they make design a gigawatt MSBR, but just the conceptual design. This is some photograph, the Ivan Wimberger. I just got a slide, a paper is for the Wimberg Foundation. Yeah, Wimberg is pioneer for many things. One of them is MSR. Yeah, this is some result from the experiment, MSR in Oak Ridge National Lab. And later means MSRE have been shut down from the middle of the 1970s. Still, there are some research activities in the world. We can show them here, the so-called MSR families. First one, used for the hydrogen and electricity production. The name is Advanced High Temperature Reactor, mainly in United States. And recently, they changed name in the FHR. And this is the so-called waste burner. There's some program in Mossad and MSFR in Europe and FS MSR in United States. And this one is used for the space reactors. Yeah, mainly, there's some design in United States. This still in United States is a combined fusion with fission. It's so-called hybrid nuclear reactors. And this is the Fuji. Fuji design is make the MSR to be chosen as one candidate of the fourth generations. One of the six. The advanced high temperature reactors design performed by the UC Berkeley's. This is the so-called baseline design. These FHRs, they combine the several major technologies together and to hide the new idea for the next generation of the reactor. It's so-called passive save power. This is from the liquid coal reactors such as sodium fast reactor and so on. And this Brayton power cycle is a high efficiency. This so-called tracer fuel. Tracer fuel provides more safety nuclear technology. And this is a very important technology, is the so-called molten salt reactors. It's a high temperature and low pressure and transparent liquid salt coolant. Based on this several kind of technologies, American scientists and make the several design for the FHR. Is a large scale, this one, and a small scale modulator reactor here, and this is used to be baseline designed by the UC Berkeley. This designed by the MIT. This too is designed by the Oak Ridge. And still, the DOE initiated a project, Integrated Research Project. It's IRP. It's performed by MIT, UC Berkeley, and the University of Wisconsin to make research of the FHRs. And this is the contents of the project. The Oak Ridge National Lab and Idaho National Lab have been engaging in this project. And the White House as advisor. The first national conference on thorium was held in 1965. ThEC12 at the CNAP. And by end of the 1970s, SINR is a former name of the CNAP, launched the research program, the production and enrichment of the uranium-233, and got 6-gram nuclear-grade uranium-233 through the ThEC method. From the 1970s, led by Dr. Jianghua Zhang, is the previous director in general of SINR. The thermal uranium fuel cycle research has been performed in SINR more than 20 years, which include the radiation experiment research of the thorium sample in high flux reactor, zero power reactor critical experiment research with thorium and uranium fuel. Thorium fuel used in the PWR and theory research on the thorium breeder. In 1980s, collaboration with Tsinghua University, SINR have performed the research on the processing thorium uranium spent field in high temperature gas cooling reactor. Here shows some history on the thorium uranium fuel and MSR research activities in, it's SINR. And actually, SINR have constructed zero power reactors. One is MSR, yesterday I mentioned, and another one is the so-called light water reactors, and have performed so many years reactor research on the thorium. This is a so-called zero power cold MSR, and built in 1970 to 1971, and reached critical in September 1971. And there's some data. Later, SINR built another zero power reactor. It's a light water reactor. And recently, there are several proposals and reports on the implementation of the thorium as a nuclear fuel have been submitted to central government from the beginning of this century. And the 3 Chinese companies launched the collaboration with SECL, the company of the Canada, on evaluating implementation of the thorium in CANDU reactor. And under the approval of the government, CAS initiated Innovation 2020 program and deployed strategic Pioneer Science and Technology Project. It's a very long name. And one of them is Advanced Nuclear Fission Energy of Tomorrow. Within, one is the TMSR. Have been approved January last year's TMSR started from then. The aim and the roadmap is to realize the thorium and uranium fully cycle mode in TMSR. And non-electricity application, electric application, the PBFHR. And to build 2 megawatt melted salt cooled test reactors and the non-electric application test facility, such as the hydrogen product produced. And the project is a long term, about 20 years. And the aim is to build 100 megawatt the test reactors. And the more detailed plans is that to build the 2 experiment reactors, TMSRS, and the non-electric application experiment facilities and build up the R&D ability, include the research conditions, key technology, and the research team for the future TMSR development. CS have started approving procedure to combine research program uranium recovery from the seawater. That's another story. One is the 2 megawatt pebble bed fluoride salt coolant reactors. We call this is the TMSR with solid fuel. The timetable, the terminal is 2011. It shall be finished. And another one is 2 megawatt molten salt reactors. It's a liquid fuel with a thorium uranium modified open fuel cycle. This with a thorium uranium alternative 1-through fuel cycle. This is the 100 kilowatt SOEC experiment facility for the hydrogen productions. It's implantation of the high temperatures. And 1 per hour, 1 kilogram, the methanol reactors experiment facilities. And 100 kilowatt CSP. That is mainly the implantation of the molten salt loop technology. The ability to be built in the future. First one is the TMSR reactor design and development. Is some physics design and engineer design and so on. Then later is the salt productive technology and the molten salt loop technologies, such as separation of the lithium-7 and purification of the fluoride salt, and design and construction of molten salt loop and so on. And the third one is for the fuel technologies, the first production nuclear grade thorium, and online chemical separation is so-called pyro process. We have began the research on this field. And fourth one is for the material. The molten salt loops need a different material. It's a key problem, the key challenge. And the production, processing, and testing of the structure material. First is the hydroxide N and the graphite. And later, we will develop the carbon-based structure material and the components for TMSR. And finally, we are developing the safety code and licensing technologies. This map just summarizes the contents I mentioned above. We will build 2 reactors. First is so-called the pebble bed FHR with a thorium fuel partly. This is the MSR with a liquid fuel. And output is high temperature. High temperature will send to deliver to the power plant and also to non-electricity applications. This is the development, the roadmap. Is a 2 megawatt, 10 megawatt, and 100 megawatt. It's so-called 3-stage. And this is the fuel cycle technologies. We start from a modified open fuel cycle. Final aim is a fully closed fuel cycle. The aim is a commercial applications of such as 1 gigawatt reactors. If we want to build this one, we have to develop it such the technologies. And we have the working breakdown. We had 3 steps. In different steps, we have to solve the different problems or develop the different technologies. And step by step, if we can solve all the problems, we can success to reach to the gigawatt level reactor. Then the team and the organization. Team is very important. And the basic team from the CNET, we have some have the appearance SSRF, SRF is a project, and we just need some engineering experience for physicists and chemists. It's very important for nuclear energy engineer. And young scientists and engineers are majority is for the future. Later I will show of the team. And also to attract excellent younger and experienced scientists, both from the domestic and abroad. This team structures. We have the several divisions, and here is a team total in the planning number to the 2015. That's a planning number. And at the moment, we have had this number. It's about 350 permanent staffs. From the beginning of the last year, within 2 years, we have had more than 300 staff already. And this is some structure of the team. This is the so-called earth structures. About half is earth, 20, run from 20 to 30. That is, I just said, younger is future. So our team very young, so we shall be had the bright future. And my urge is just in this very narrow place, very, very narrow. It's a little below the 60 years old. And we also have had some experience, science and scientists and engineer. Some of them is, most of them is larger than 60 years old, and some of the older than 70 years old. But I still know that at that period, China have trained some of the experienced, the scientists and the engineer. And also we have other staffs. It's almost half, is about 40% is a PhD. And others is so-called, because we have the many engineer. This is the so-called its organizations. We have a center. This center is funded by CS and led by CS directly. And we have several departments here. The center have the board. And the center here, now I'm the director of the center. And Dr. Jiang is present here for this project. Yesterday he gave a presentation for the outlook of the China energy. And we have so many divisions. Total, we have 8 divisions together. Last year we have 6. Maybe next year we have maybe 10, maybe more than 10. Also have the other institute engaging in this project. Total is about 10. And such as the organic chemistries and the metallurgy chemistry institute and so on. They in charge of the different missions, especially for produce the material. And finally, I just show some photograph about our progress. This the Shanghai map, and the synapse there are 2, the compass. Now we are in this place, and this is the compass for the nuclear energy. This compass for the south. And now we have an old compass. We have built some the lab, and recently we have the competition platform for the design of our project. And we have built the laboratory for molten salt chemistries. And also we have the molten salt loop development plans. This is the first one, 1, 2, 3, 4. And this is for the reactor. We have finished this one. This year I finished this one. And last year this one, and so on. And this first rope, and this second one is the design. And very salt pump, we are building the prototype. This is separation of the lithium isotope. This is the material developing is a roadmap. I have just shown we have built our own Hastelloy and alloy, and also we purchased from the United States. And also we built silicon carbon the material, and we have tried some new nickel-based alloy elements, and also we built some composite based on the carbon-based material. And then some the material technology, the roadmap. There's some experiments, and this for the process, parallel process. Parallel process is very important for the serum implantations. We have set some guideline, and we try and focus on the effort on these two methods. And we have built some the experiment facility and have done some experiments. And also we discussed with American scientists with the DOE about the possible collaboration between us. And this is the so-called 2 megawatt test water. This is our design for the test reactor. The main parameters. We have make the international review meeting. The most experts from the United States and one from Russia. The pebble bed, you can have the two choices. One is the older bed, and another one is the random bed. Recently, we combined the two design and optimize the design of them. Still, because drugs is for the initial rest heat remove systems is based on natural cycle. We are make design of the drug system, and we will build the test facility next year. And also we built our own accelerator to measurement some of the data for the cross-section on the surface. And this is some design. Of the project, the budget is actually very, very good. Within 5 years, we have the almost $100 million US. And we hope we can have the start for the molten salt reactor research, and also for the serum implantation research for the future. Thank you. Thank you for your attention.
Presented a wide range of projects, and you have questions?
Thank you very much for your wonderful presentation. My name is Takashi Kamei, coming from Kyoto, Japan. I have 3 simple questions. The first question is, how many capacity are you going to implement thorium molten salt reactor in China? For example, in 2050. This is the first question. The second is, what kind of fissile material are you going to use? For example, plutonium or the uranium-235 or uranium-233 with thorium. The last question is, if you use uranium-233, how you obtain uranium-233?
Yes, first is the equipment.
How many reactors are you going to use?
Equipment for all the test reactors.
in China.
Yeah. At the moment, almost all the equipment have been built in China because we cannot purchase the equipment, commercial available equipment at the moment. But such as the control and the measurement system, maybe we can purchase some commercial available. But it's equipment for the core. We have two built by ourselves. But we have a collaboration with United States, with Oak Ridge, with Oak Ridge National Lab and Idaho National Lab, but just a discussion. And the second is fuel. And I just show. First one is so-called solid fuel. Solid fuel is a tracer fuel. Tracer fuel, this technology has been developed during last 20 years in China, used for gas cooling reactors. But we have to make some upgrading, which can be used for the molten salt reactors. At the beginning, mainly used for the uranium. This is the common sense. Because the thorium is the second steps. So I think it's all the roadmap is start with uranium. In China, we have no so many platform 239. So maybe we can have some uranium 235 to start all the reactors. Later, we will put some the thorium, and we have no plans to breeder thorium 232, and that means we have no plan to get more the uranium 233 from reactors. So we just burn it out. And last one is about the uranium 233. Only in United States they have pounds uranium 233. Some American scientists suggest to me to discuss with the DOE, ask them to sell that uranium 233 to us. Maybe later we can discuss with them because they useless. And they know all the project. And also they hope to collaborate with us, and maybe in future they also share the common sense for the importance of the thorium. At the moment, Americans have no any plans to make research and applications on the thorium. Okay?
Thank you very much.
Jean-Pierre Revol from CERN. Your statement by Carlo Rubbia is only true if you assume breeding. You just said that you don't plan on breeding the fuel. So I'm wondering, you're going to run out of fuel very soon.
Yeah. Actually, nowadays the idea, the breeding, have been changed from we said the many years ago. Now the breeding idea is you can get more fuel. Like more, such as C have to be the larger than one. Actually, you can calculate. If you just want to use thorium as a fuel, you don't need the C larger than 1. Less than 1 is okay. Maybe 0.8. You just consuming the uranium together with the thorium. But only fuel the uranium-235 and a lot of the thorium. It's okay. So that's I mentioned we have no plan to breeder to build the breeder thorium reactor. Maybe you know that the history, the Oak first they make design of the MSBR. MSBR is a super breeder. The C is 1.007. It's compared with the sodium fast reactor, they fail. The main reason is that this C is too low. So if you consider from energy point of energy, you don't need so high the C. It still works. That's all.
Thank you very much, Dr. Chu. Okay, the next presentation.